All right. Hopefully it'll continue to work now. Okay, so we're comparing and contrasting Euler's equation with Bernoulli's equation. And so Bernoulli's equation is here. I showed it on the whiteboard during the lab yesterday, but it's a way of saying you consider the pressure, elevation, and velocity at one location in the flow field, and you compare them to the sum of those three parameters at another location in the flow field. Now there's some very important restrictions on when we're able to apply it, and so we have to be careful about the physical situation that we're trying to apply Bernoulli's equation. And the further we get away from the ideal constraints of when it's applicable, the worse it will be at predicting performance. In fact, the restrictions that we have for applying Bernoulli's equation in some ways are mutually exclusive, which means that there's really no perfect situation where Bernoulli's equation will apply perfectly. And so there are some errors that arise that we won't be able to really address until we look at energy losses in Chapter 7. Now here are the conditions where we can apply Bernoulli's equation. It actually comes from starting with Euler's equation, but then applying it under circumstances of steady flow. So that means that conditions aren't changing over time, along a streamline. And what we mean with that is that if I have a pipe section that's contracting like this, what we could do is we could draw in streamlines. Just sort of gives you an idea of the path or the route that's taken by the flow in this section. And so I'm drawing these dashed lines to indicate streamlines. And there's one in the middle as well. All right. So the restriction of applying Bernoulli's equation along a streamline means that if you started here at the top part of the section before the pipe had contracted, you couldn't apply Bernoulli's equation at the bottom part of the pipe later on downstream. We assume that flow is going here from the left towards the right. We couldn't choose this as location 1 and location 2 because they're not on the same streamline. And we'll get into why that is a little bit later. But for Bernoulli's equation to have any predictive power, we have to apply it along the same streamline. And so we could either do it like this, which is shown, or most commonly, we would just say, let's apply Bernoulli's equation along the center line of the pipe. Because if you go along the center line of the pipe, then a few things are going to simplify in Bernoulli's equation. If we go back to see it here, along the center line of a pipe, if the pipe is horizontally oriented, then Z1 would equal Z2. And so not only are we satisfying the requirement that we apply Bernoulli's equation along a streamline, but also it's simplifying Bernoulli's equation and taking out that elevation parameter. Okay, so steady flow along a streamline. The next restriction is that Bernoulli's equation should be applied when the flow is incompressible. So we're talking in this course mainly about two different kinds of fluids, liquids and gases. Of the two, which do you think better honors this requirement that the fluid should be incompressible? Liquids, definitely. Now remember, earlier in the semester we talked about how even liquids themselves can be compressed, although it requires enormous pressures and the reduction in volume is very, very minor in comparison to the how easily compressed gases are. But so what this means is that we're going to have some mistakes if we apply Bernoulli's equation to gases that are experiencing compression as they flow. And so a section like this where the diameter is changing could cause a change in the pressure because of the molecules getting closer together, rather than just a change in pressure we'd expect from the Bernoulli effect itself. No reason. No reason. It just means velocity. We could write it as lowercase and it would still mean velocity. No, sometimes when we have volume, we would put the cross through it, you know, the strike through the V. But most of the time, we just sort of interpret whether it means velocity or volume from the context in which it's supplied. Go ahead. Okay, so the question is, if we're applying Bernoulli's equation at the center of the pipe, you'd use the velocity at whatever location you're choosing for the point of application. And so earlier I drew, you know, what if we wanted to do Bernoulli's equation here, where this is 1 and this is 2. We can do that as long as we're on the same streamline. The velocity near the edge of the pipe isn't going to be the same as the velocity at the center line. So we can find out what's the velocity here, maybe through a velocity profile if conditions are laminar, or through a measurement. So it doesn't have to be the center line velocity. And oftentimes what they'll do is use the average velocity for the cross section. And the easiest way to find the average velocity for a cross section is to look at the flow rate and divide it by the area through which flow is traveling. So that's kind of a common approach, is to use V bar, which means the average velocity. But if we have more specific information, we can use that too for a certain spot. Okay, so back to the idea of incompressible fluids. So if you use Bernoulli's equation for gases, which are compressible, then you can expect some error from that. What Bernoulli's equation predicts may not be exactly what you measure in the lab or in the field, because of that deviation from the required assumptions behind Bernoulli's equation. So we've done 3 so far. Steady flow along a streamline for an incompressible fluid. And this last restriction is that the fluid we use should be inviscid. Now, most people don't know what inviscid means. It means a fluid with no viscosity. Can you think of any fluids with no viscosity? Neither can I. So Bernoulli's equation never applies, right? All right. Well, we could just throw up our arms and go take a nap, but we won't do that, because even though Bernoulli's equation never applies perfectly, it often applies good enough, right? It's still useful even though there's no fluid with no viscosity. But let's look at it the same way we did before. When we were talking about incompressible, we said, well, between gases and liquids, which is like the worst violation? And it's gases, because of the two, liquids are more incompressible. So we'll get some more accuracy as far as this assumption is required when we use liquids. But then viscosity, maybe you haven't developed a sense for it yet, but in the back of your book it has tables of viscosity, and gas viscosities are much, much lower than liquid viscosities. And we can experience that as we walk through a gas, as we walk through the air. There's a lot less resistance to our movement compared to when you're moving through a liquid like water. So it's kind of ironic that in one sense Bernoulli's equation is better for liquids because they're more incompressible. Then on the other hand, Bernoulli's equation is better with gases because gases are closer to the inviscid assumption. So what it really means is that we have to be careful about how we apply it. The assumption about inviscid, or a fluid with no viscosity, is all about trying to limit the effect of frictional losses. And so here in this drawing I've got location 1 and location 2. If we have these two locations really far apart, the effect of friction is going to be more pronounced. And so this weakness of trying to model what's happening with the assumption that there's no fluid viscosity and therefore no friction losses, if we bring the 2 points closer together, then friction losses are minor and we get in less trouble for violating that assumption. So you can sometimes avoid the trouble of violating your assumptions by being selective in the circumstances that you apply the equation. So are there any questions so far? Yes, go ahead. No, it's also applied to air. It can be applied to like oils. It could be, you could apply it to even very viscous fluids like glycerin, but it has to be under the right circumstances. And so we'll get a sense for how different Bernoulli's equation predictions are from reality in Chapter 7, because here's Bernoulli's equation. It looks very similar to something later on we're going to do called the energy equation. When we're doing the energy equation, we're just correcting for the fact that there are losses as the fluid goes through a channel. Some distance downstream, there's energy losses. Bernoulli's equation says there's no energy loss between point 1 and point 2. It's saying there's no turbulence that's causing energy loss. There's no pipe friction that's causing energy loss. It's just a perfect conversion of all of the potential and kinetic energy at 1 into the same amount of combined potential and kinetic energy at location 2. That's true. Yeah, there's the influence of friction is less at the center line, but remember, when we usually apply Bernoulli's equation, the most common thing is to use the average velocity rather than a measured velocity. And so if you're using the average velocity, it kind of takes into effect the entire cross section, the top, the bottom, in the middle. Yes?
So we need to find the velocity in 2 locations. Do we need to take like intermediate points so we will achieve next?
I like the way you think. You're trying to solve problems. So you're saying if you wanted to know the pressure really far downstream, could you break it up into smaller segments? Unfortunately, that wouldn't get you around the problem. If you broke it up into small segments, there's still the cumulative effect of adding them all up. You're assuming essentially that there's no energy loss in a small section, no energy loss in a small section, no energy loss in a small section, and so over the entire distance you're still assuming that there's no energy loss, and it's not any more accurate. The only way it becomes accurate is when the actual point of interest isn't very far away from where you're starting. Mm-hmm. Yeah. Was there one more question in the back here? Yeah.
Will we ever have to apply Bernoulli's equation over like a certain height when we're taking into consideration friction?
What do you mean have to? Like gun to your head?
Is it always going to be said that you use Bernoulli's equation once they're like side by side?
Usually, like in the types of examples and questions I'm going to be asking you, it'll be over short distances, or I won't even tell you what the distance is. Like we've got an example today where I've got a picture of something similar to this, and I don't even say the length between them because we have no way of correcting for that distance, and so we just ignore it entirely. Okay, well, let's talk about models. A model is some sort of a simplification of reality. It's a way of conceiving of a system in a more simple way. And so here on the bottom image is a picture of a full-size prototype, is what we call the full-size version. And up above is a model. And models are usually made smaller than prototypes just for ease of construction, ease of measurement. Anybody know what kind of plane that is? That's right, it's a 747. You can tell because it's got like the second row of windows. An Airbus 380 also has a second row of windows, but it goes all the way back. This one just sort of has near the front of it. So here's a 747 that's being modeled in a wind tunnel. And there are a lot of reasons why you would want to use models. They're cheaper to work with than full-size prototypes. If you want to make a change in the wing angle, for example, it's a lot easier to do that with a clay model than a full-size working aircraft that maybe costs millions of dollars. Bernoulli's equation is itself a model. Models aren't just physical things, they're also ideas or concepts, a way of expressing reality in kind of a simplified way. And so Bernoulli's equation is a way of modeling what happens to elevation and pressure when velocities are changing. Now Bernoulli's equation is a certain kind of model. It's a fundamental equation. And so that means it's a model that's grounded in the most basic precepts of science, and it's based on a knowledge of the governing laws of physics. Now contrast that to this kind of model, which from the looks of it, it's a model that has to do something with the available range of an aircraft, and it looks like it's a function of how much fuel they've got on the aircraft, the weight of the aircraft, and some constant. So this is an empirical equation. And so it's a model that's just based on observation rather than based on some underlying governing principles. It's just based on lots of data that they fit a best fit line through sort of a best fit curve using Excel or something like that. And so whether you're using an empirical equation or a fundamental equation, models are a way of representing systems. And we apply them within certain constraints. So the boundary is, in a physical sense, that the walls of the wind tunnel are the boundaries of the physical system that that model is applicable for. Bernoulli's equation, we've talked about the boundaries of Bernoulli's equation is the limits that we can safely apply it. You know, along a streamline for steady flow with an inviscid fluid that's incompressible. Those four characteristics of when Bernoulli's equation would truly apply. The variables are the things that we expect to observe changes in for the model. So the variables for Bernoulli's equation are going to be the pressure, elevation, and velocity. Variables, though, are different from parameters, which are system constants that usually don't change, or if they do change, are only affected indirectly by things like temperature, and we don't have necessarily a direct control over it. It's sort of not the input variables, but just taking, for instance, the unit weight of liquid, or gravitational acceleration, or the viscosity. They may vary a little bit because of changes in temperature, but they're not the main things we're trying to predict with Bernoulli's equation. The things we're trying to predict would be elevation, pressure, and velocity. Now we'll come back to talking about models in Chapter 8, the very last lecture of the semester. But it's useful right now when we're starting to have a lot of equations coming at us to think about the role that models have in engineering and being careful and understanding them rather than just plug and chug. You know, having an equation and putting the numbers into the equation is something that we really, makes us feel warm and fuzzy. It's easy to do just because it doesn't require any judgment or understanding. And that's the sort of thing that an engineering technician can do. But what you're aspiring to do is a step above the engineering technician. An engineer has to understand where the model came from and what the weaknesses of the model are and apply judgment rather than just a mechanistic approach of plug and chug, as they say. So Bernoulli's equation is a model, and it combines what we call kinetic pressure and piezometric pressure. This is just a different way of conceiving of the same equation. I've already showed you Bernoulli's equation, the bottom one, in terms of head, elevation head, pressure head, and velocity head. Each of these three terms, when you look at the units, are going to have units of length. For instance, if you have pressure, which is newtons per meter squared, and you divide it by unit weight, which is newtons per meter cubed, then the result of that would just be meters. Of course, elevation is meters, and so on. So this version of Bernoulli's equation is probably the one that I use most often, and I'm not sure why. It's what I use most often. This is the identical equation, just if you've multiplied each of the terms by the unit weight. And so this is in terms of head, this is in terms of pressure, and each one of these three terms are going to have units of pressure in the top. Keep in mind the limitations: steady flow, incompressible fluid along a streamline and a fluid that has no viscosity. Here's a diagram that we've seen before when we were talking about convective acceleration. Remember, the definition of convective acceleration is the velocity at a certain point multiplied by the velocity gradient, the change in velocity with respect to position. So du dx multiplied by u at a certain spot. That'll give us the convective acceleration. And where the acceleration is happening the most, that's where you're having the largest or the quickest change in pressure as a result. So I'd like you to get your hands dirty with Bernoulli's equation. Here is a pipe that's changing diameter. And I've given you the velocities. I don't expect you to calculate those with Q equals VA. They're given directly. But just to give you a sense for how much the pressure is changing as a result of velocity changing. Now, when I create examples, I have to be really careful to create examples where there's actually an effect that you can observe. And so this is a really radical transformation in velocity. If I didn't have it go from a pretty high velocity, so 5.5 meters per second, I mean, that's really moving along to be able to cover 5.5 meters of ground in a second. So this is a high velocity transitioning to a really low velocity. Let's see what kind of effect that has on pressure. In the problem statement, it says that the pressure at 1 is 400 kilopascals, and this is water that's flowing through the pipe, and so you can use the standard unit weight of 9810. Calculate P2. Okay, we know the pressure at 1, the velocity at 1, the velocity at 2. We don't know the pressure at 2. And by inspection, just by looking at it, it seems that the horizontal orientation means that we can say Z1 equals Z2. So that's going to simplify Bernoulli's equation from what's written here. It's going to make it so that we could rearrange and solve in terms of P2 by just adding together the pressure head and velocity head at 1, subtract the velocity head at 2, and then multiply all of that by the unit weight of the liquid. Okay. So when we substitute in the values, I like to do all these intermediate steps because I want to know where is the pressure coming from. Like, why is there a certain pressure at 2? And so most of the pressure head is because there was a fair amount of pressure at location 1. It's not like there was a lot of head there from the velocity. This 1.541 meters shows how much energy was tied up as velocity before. When it was going 5.5 meters per second, that seems really fast, but that 1.54 meters of energy is just a tiny fraction of the amount of energy that exists in the form of pressure, since in the pipe it was 400 kPa to begin with. So having these intermediate steps is sometimes useful to say, you know, like, what's the range of energy you've got to work with if you're expecting to make some sort of a change. So how much velocity head is there at 2? Hardly any. This 0.0206 meters says that, you know, if I made that example, the velocity at location 2, if I took it down to 0.1 meters per second, instead of 0.6, that's going to have virtually no effect on the pressure, that further reduction from 0.6 to 0.1, because the amount of energy that's in velocity head is already so small to begin with at location 2. So we can put it all together and find that the pressure at 2 is 415 kilopascals. And that's Bernoulli's equation. 450 kilopascals, asterisk, as long as this is steady flow and we're applying it along a streamline. For an inviscid fluid, well, this is water, which isn't exactly inviscid, so we feel a little bit guilty for that, but we'll get over it. and then incompressible. And water's pretty good at being incompressible. Yes? That is a little counterintuitive, right? That's a great question. Let's think about that. Because normally, like if you just thought of it in qualitative terms without an equation and without a calculator, maybe your brain would think, well, you've got this enclosed pipe and it's all bottled up, and then the water, it opens out and now it's free, and so the pressure should decrease because it's like less confined than before. I mean, conceptually, that's oftentimes the idea that students have. But it's just all about the energy, and where is the energy and where can it go when there's a change. We know that expanding that pipe must slow down the velocity. There's no way around it. It has to slow down the velocity. So at location 2, less energy is going to be in the velocity head. So it has to go somewhere. It can either go into the elevation or into the pressure. And it can't go into the elevation because the 2 points we were looking at were at the same elevation along the horizontal plane. So the reason why the pressure goes up is there's just no place else for that energy to go. It has to go into the pressure. Yes?
So this would be assuming that the angle at which the pipe increases is small enough where, like yesterday, the rainfall is on the degree.
Mm-hmm. All right, so you're saying, like this, it seems like it's getting wide pretty quickly. It's not tapered gradually. The main reason in the lab why it's tapered gradually is to avoid turbulence. Now, we're not accounting for turbulence in Bernoulli's equation because turbulence is a kind of energy loss. Now, you were talking about, like, would there be, you're envisioning in your mind like a lot of swirling turbulence, right? Like vortices and eddies there. Yeah, it'll cause that. But it's not like there's going to be air in there because of those. It's not going to introduce air because there's lots of turbulence. But there would be energy loss, and Bernoulli's equation would do a worse job of predicting what's happening for a rapid transition than it would with a smooth transition.
You can still use it, but it just does a worse job.
Mm-hmm. Yep. So you're right to start thinking about, where is energy going to be lost? It's going to be lost partly due to pipe friction, which I've already talked a little bit about. Like, you want your 2 points to be relatively close together to minimize the pipe friction effect. But you've got a great point that these are called local losses. They're places where some sort of a change in a fitting or water flowing through a valve, that it's changing direction in the valve, or an elbow in a pipe. Those are all things that can induce turbulence. And if you've got local losses that aren't accounting for some loss in energy, in Bernoulli's equation, there would be a difference. Mm-hmm.
So if you did that in the lab, do you feel the pressure difference and then velocity decrease? Like you were shooting out of the height or something?
I don't know if you could physically perceive of the pressure difference like with the skin, but it can certainly be measured. Do you have lab on Monday?
Yeah.
You will see, like the experiment you're running with Dr. Ford on Monday, you will see with your eyes the effect of the pressure change. What we do is we connect a piezometer to a pipe section that contracts and then it expands again. And what we observed by connecting these little tubes, if you remember, those of you who had the lab yesterday, the little tubes, the water went high when the diameter was wide, but then the little tubes at the throat section of the pipe, the water didn't go as high because the velocity was decreasing. But then when it expanded again, then the tube is high again. So you can actually measure with a piezometer or some other pressure measuring device the effect of the velocity change. It's physically observable. Are there other questions about this?
Would the velocity in that situation at the center of the pipe where the neck's happening, would it be greater than it would be?
So you're saying if you're talking about the center line, so here is one location and here's another, yes, the velocity is definitely higher here because the diameter decreases and the reduced cross-sectional area forces the velocity up.
And that's the reason why there's a change of pressure.
Mm-hmm. Yep, it's because the velocity is
This
changing.
equation's just assuming that conservation of energy.
That's
going
right.
on the whole time?
Mm-hmm.
Okay.
Yeah, it's saying all of the energy that was at 1, it's still there at 2, and there's no losses in between. And later on, we'll use this and add on some additional terms to account for the types of losses that we commonly experience, the frictional losses and the fitting losses that we call minor or local losses.
Energy in equals energy out.
Right. Mm-hmm. All right. Great. All right, so I want to put a table on the whiteboard. I want to always sort of keep you with context in mind. So we are going to have acceleration type, and then we're going to talk about the flow type, velocity change, with respect to some parameter, and then the model that we use to do calculations. All right, so if we have gravitational acceleration, so gravitational acceleration, what type of flow do we have? There's no flow if it's just only gravitational acceleration. We would have no flow because the conditions are static if only gravity applies. So in a situation like that, velocity is changing with respect to nothing. That column is going to apply for other things. But what's the model that we use for delta p when it's gravitational acceleration? That's right, hydrostatic equation. So delta P is delta H times gamma. All right. So what about if we have local acceleration? So local acceleration is associated with what type of flow? They're steady, unsteady, uniform, non-uniform. So which of those describes the case when you do have local acceleration? What is it? Unsteady. Now, there may or may not be uniform flow. You can have unsteady non-uniform, you can have unsteady uniform. But unsteady flow is what results from local acceleration. And unsteady flow means that the velocity is changing with respect to time. Time is the parameter that velocity is changing with respect to. And so that's when we use Euler's equation. So a change in piezometric pressure divided by dl, and its density acceleration times L. So we can expand that out to tell us how the pressure change is affected by the unsteady flow. What we're talking about today is when we have convective acceleration. Convective acceleration is when we associate that with non-uniform. It's velocity change with respect to the position. And it's something more specific than just position, because remember that velocity is a vector, and so it has magnitude and direction. What we're talking about with convective acceleration is it is the magnitude of velocity that's changing. So velocity is changing with respect to position, and it's the magnitude of the velocity that's changing with respect to position. And what we use for that is Bernoulli's equation. So P1 divided by gamma plus Z1 plus V1 squared divided by 2G is equal to P2 divided by gamma plus Z2 plus V2 squared divided by 2G. Several years ago, I gave a challenge to students, and I told them if they didn't use any equation sheet for the second exam, I'd give them extra bonus points, because there's so few equations that you're going to be using on the second exam. And there were several students who took the challenge, and they did just fine. In fact, even before the bonus, they did better than the students who did use the equation sheet. I think it's probably self-selection. They were the ones who felt confident to begin with, so they knew the material. It's not that avoiding the equation sheet was the reason they did better. But there's really not a lot of equations on the second exam, because it's big ideas mostly, rather than lots of little empirical equations that we're using. Okay, should I do that again? Oh, I'll have to consider it. If it was a bonus, it would be really small. Yeah. All right, so gravitational acceleration, local acceleration, convective. Later on, we're going to also talk about centripetal acceleration. I'll put it on the board now, although I'm not going to show you the model for it because I don't want things to go too far off the rails. Centripetal acceleration is associated with rotational flow. And when we were looking at flow types, we saw examples of rotational flow. It's sort of like liquids that are going in a circle, and in a situation like that, you have an acceleration because the velocity is changing with respect to position, but it's not the magnitude of velocity that's necessarily changing, but rather it's the direction component of velocity vector. So not on Tuesday, but a week from today, on Thursday, we're going to talk about rotational flow and how that affects pressure and elevation, spinning around, liquid spinning around in a circle. But I just wanted to put it on there because there's a way to sort and organize these equations that you're going to be seeing in Chapter 4. It's all about how acceleration changes pressure. And the acceleration is of different components. It may be acceleration with respect to time, acceleration with respect to position, but it's important to keep that in mind. Let's look at another example. This is one that students often struggle with because of the device. Like, what's happening with this device isn't immediately clear. So let me try to break it down for you. We have a contracting pipe section, and as we've talked about before, when the diameter decreases, that increases the velocity. Now, it's air that's going through here. There's a water manometer that's measuring a change in pressure, but it's air that's flowing through this contracting nozzle. We have three locations of interest. There's location 1, and what we can say about location 1 is that the velocity of the gas is low. And then here at location 2, the velocity of the gas is higher. Now remind me, what happens to the pressure if the velocity of the gas is going up? Right, so the energy required for the velocity to be higher, it has to come from somewhere. And in this case, it's coming from the pressure. It's all on the horizontal plane, and so the z component of Bernoulli's equation we can ignore for this example. Okay, so we've talked about position 1 and position 2. Now, inside the tube, conditions are static. If we were to zoom in on what's happening at that tube opening, we'd have a stagnation point. And so there's some energy in the velocity just outside of the tube. I'll illuminate it with the laser here. So just outside of the tube, the air still has velocity. So think of it, there's some energy trapped in that velocity. But then when that streamline dead ends at the opening of the tube, all of that energy that was as velocity is suddenly exchanged into a little more pressure, an increase in pressure. And so inside this tube, there is no airflow in the tube. Conditions are static. But if you look at this deflection of water, what's causing the fact that the water level isn't the same is because there is stagnation that has converted some velocity into an increase in pressure. So it's not the fact that the velocity is higher at 2 that makes the pressure higher on this end of the manometer compared to that one. It's because of the stagnation effect that's happening. Now here's some information about this device. The cross-sectional area at 1 is double the cross-sectional area at 2. And so we don't actually know what the diameter or the area is, but knowing that it's double allows us to say something about the relative velocities. It allows us to say that the velocity at 2 is twice the velocity of the gas at location 1. Okay, so we have that relationship known from the cross-sectional area relationship. This is air that's going through, and we know the density of air, and we're going to have to assume that the air is not compressed, or whatever the opposite of compressed is, expanded. It's not undergoing any sort of change in density as the air flows through the nozzle. Remember that we have an incompressible fluid here, or at least we're going to pretend like the air is incompressible. We want to know what's the velocity at 2. And this manometer is a way of measuring the velocity. So here's what you're going to do in this example. You're going to use Bernoulli's equation, and you'll notice that what I've said instead of P1, Z1, P1, Z1, and V1, instead of saying all those things are equal to conditions at 2, I'm saying, well, consider what's happening at the tube. Use that. However much energy there is at 1 is equal to the energy at 2. We assume perfect conservation with no losses. And the same thing is true between location 2 and just inside the tube. All of the energy that was there on the left side of that opening still exists on the right side of the opening. It's just transformed from a little bit of velocity into a little more pressure. There's a change of energy state from the outside of the opening to the inside of the opening. So you can use Bernoulli's equation to tell you how the pressure inside of the stagnation tube is related to the velocity inside of the pipe section. The other thing, this is kind of like a combination. A lot of these problems moving forward are going to be two ideas mixed together. So here's the the hydrostatic equation, which applies inside of the manometer, combined with Bernoulli's equation. And so the manometer equation is going to tell you the relationship between P1 and P sub T, which means the pressure inside the tube. So you're going to use the manometer equation to relate P1 and PT. What's the velocity inside the tube? What's the velocity inside of a stagnation tube? 0. Conditions are static. There's no flow velocity. So V sub t is 0. All right. So we want to find the velocity at 2. What you have to do first is find the velocity at 1. And once you know the velocity at 1, then you can find the velocity at 2 with this relationship from above. All right. So I'm going to let you mull that over for a little bit, how to combine it all together. I seem to remember there was one more tip I was going to give you. The density of air is known, 1.2 kilograms per cubic meter. And so from that you can get the unit weight of air. You just multiply the density by G, and you can get the unit weight of air. And obviously 1 and 2 and T, it's all on the horizontal plane, so the Z's are equal for those. Okay, I thought of one more thing I wanted to tell you about in this problem, and that is, let's say that we're applying this at location 1 is on the center line, and location T is also on the center line. assume that the pressure doesn't change very much as you go down from, for example, from here at 1, which is on the center line, to the water surface. We don't know how far that is. And so if we wanted to apply the hydrostatic equation to find the relationship between the pressure at 1 and the pressure at T, then we'd have to keep track of, well, how is the gas affecting a slight increase in pressure? So just assume that this manometer, which is connected to the contracting section, assume that this manometer is telling you the difference in pressure between 1, which is at the center line, and T, which is at the center line. So we're assuming that everywhere on this side of the tube, the pressure is the same, and here at the water surface, the pressure is the same everywhere in that tube. And then here at the water surface, the pressure is the same at the surface as it is at the center line of that gas carrying tube. And that's an okay assumption for us to make because it's probably not a big distance, and pressure doesn't change that much when you go up and down through a gas, not like it does through the water. All right. Just that was the one other hint that occurred to me. For the velocities? No, that's not right. The manometer fluid is water, and so you use the gamma should be 9810. Okay, so the first thing we can do is find the difference in pressure between the 2 points, between what's in the tube and location 1. The manometer tells us the pressure difference is 981 pascals. So if we rearrange Bernoulli's equation so we can use that, here we do some rearranging of Bernoulli's equation. Here's the simplified Bernoulli's equation once I canceled out Z1 and ZT, and I also canceled out VT because conditions inside of the tube are static, and so the only 3 parameters remain. And I can rearrange them. Just for simplicity, I multiplied each term by gamma. Like there's the 2 ways to look at Bernoulli's equation. One is in terms of pressure and one is in terms of head. So I wrote this in terms of pressure because I know I'm going to have PT minus P1 from the manometer equation. So once I've rearranged Bernoulli's equation in terms of PT minus P1, then what's on the right side is just the density, the velocity at 1, and divided by 2, where it's the velocity at 1 that I'm trying to find. So then I rearrange it again so that I can solve for the velocity at 1. And that should be 40.4 meters per second. And then I can substitute that, sort of not showing on the page. Let me write it on the board. In the original given information, we knew that the area at 1 is double the area at 2. So V2 is 2 times V1. And so that means that it's going to be double the 40.4 meters per second. So V2 is 80.8 meters per second. And that's our final answer, 80.8 meters per second for the velocity at 1. Oh, sorry, the velocity at 2. Now, you didn't necessarily have to make this same conversion that I did in this step. You could have left it in terms of head rather than in terms of pressure, and you can still make the substitution, rearranging this in terms of P1 minus PT divided by gamma. Okay, I want to show you a couple of tips on the Euler's equation problem that you've got on your next homework assignment. You've got a tank of water that's accelerating in two directions simultaneously. It's accelerating to the right at 1g, meaning 9.81 meters per second squared. And then it's accelerating down at 2/3 g. The dimensions are given in the problem statement. It's a tank that's 3 meters tall and 2.5 meters wide. And then they've labeled 3 locations, A, B, and C. And with the specific gravity being 1.3, that means that you can calculate the density and the unit weight based on the given specific gravity. This is an Euler's equation problem because it's experiencing a local acceleration. They ask you to find 2 things in the problem statement, and the order that they ask you to find them is actually backwards from what makes the most sense. If you solve it in the order that they describe, you'll get kind of frustrated to begin with because they say find PC minus PA and also find PB minus PA. Well, you can't go from A to C in a single step because there's acceleration in 2 directions. So what you have to do is break it up into pieces. First of all, find the pressure difference between A and B. And so you do that by applying Euler's equation with the vertical acceleration. And so it's actually this second step that you should do first. Then, after you found the difference in pressure between A and B, then you can handle the horizontal acceleration, that 1g to the right. And once you find the horizontal acceleration's effect on the difference in pressure between B and C, then you can combine it together. So you find the difference from A to B, the difference from B to C, and then pressure difference between A and C is just combining those 2 intermediate steps together. Yes?
Once you have your change of pressure, can you solve that using Pythagorean theorem?
No. No. I've seen lots of students try that method, and I've never seen anyone get the right answer with it. So
Does that not work?
that's a good question. I think it might be because the pressure change isn't linear between the 2 points, but it is linear in the direction of acceleration. But what I do know is you have to break it up into the directions that the acceleration is actually applied. And it's applied both in the x direction and in the y direction. So if you do it in those 2 steps, then you'll be able to get the pressure change between A and C. So let's look at the announcements. These weren't in the recording because the sound was off at the beginning. Your homework assignment is due on Tuesday, and then we'll have our second quiz in class on Thursday. We'll continue talking about more Bernoulli's equation on Tuesday. Right now, it's only this last problem, 49, that's Bernoulli's equation. I think you'll be able to apply that without any trouble. So I'll see you on Tuesday.